Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 4, Contextual Applications of Differentiation. Today's topic is 4.6, where we're approximating values of a function using local linearity and linearization. Enjoy today's notes. All right, for 4.6, approximating with local linearity, we're going to start off with talking about the tangent line of a function f of x at x equals a can give you an approximate value of f of x for points close to x equals a. So again, if you have a tangent line on a given function, you can use that tangent line to approximate values of other values of f of x that are close to where that tangent line is at x is equal to a. Now, before we get into this, I'm going to talk about something we're going to discuss sort of as an introduction more into the next chapter. But in chapter 5, we're going to talk about this word that is called concavity. Concavity of a function. So concavity refers to the curvature of a function. We talked previously about, whether a function is increasing or decreasing. The concavity talks about how the function is curved. Now, there are two cases that we generally talk about if a function has curvature. One of them is what's called concave up, which simply means that the function is either all or part of a U-shape. So a U-shape. So this, as we can see right here, is this U-shape. We would say that every point on this function right here, on this, would be considered concave up because all parts of this function are making that U-shape. It's curving upwards. So concave up means that it's curving upwards. It's got that U-shaped curvature. If something is concave down, then what we generally say is that it has an N shape. So it has an N shape, like a lowercase n. And as we can see, this sort of looks like a lowercase n here. It is curving downwards, so therefore we say that this is concave down here. Now, as I mentioned, it could either be the whole U shape or the whole N shape, or it could be part of it. A function, that if I were to graph it that were to look like this, where it is just this part of the line, if we were to say start there and move upwards, this is still considered concave up because it is part of that U-shape, right? It doesn't. If we were saying that this is like a parabola like we've got right here, this is only part of that parabola, but still points here because this is curving upwards would still be considered concave up. Now that we know what concavity is, right, this curvature of a function, we plug, I guess, for next chapter, we'll be talking more about how we can tell the concavity of a function using derivatives. But for now, we're going to see what we know about functions based on their concavity, based on them being concave up and concave down. Now, this statement that we said before, right, if we have a tangent line on a function, that it can give you an approximate value of f of x for points that are close to where that tangent line is. Specifically here, if this were my function f of x, if this is my function f of x, and I were to draw a tangent line right here, right, our tangent line that we would have would be, would have the same slope of the function at that particular point, right? This is my tangent line. And the thing that we would be approximating, if this is my point here, x is equal to a, and that's where the tangent line is coming off of the function, what we could do is we could say, if we went along the tangent line, that this point on the tangent line would approximate the x value for that given function. Now, one key piece of this idea, right? We could pick really any point on this tangent line and say, hey, that's an approximation for f of x. But a general key concept for this idea is that the closer the point is to x equals a, the better the approximation it will be. The better the approximation will be. And the reason for this is, the farther you get away from this tangent, this tangent point, a point of tangency, the more time and opportunity it has to get further and further away from the tangent line, right? We see that the distance here is really close between the function and the tangent line, while if we get over here, the distance is increasing and increasing even further and increasing even further. And if we go all the way down here, that distance is really far from the tangent line to the actual function. But if you get close, if you get close to the actual point of tangency, that distance is very small, so the error is very small as well. So general, the closer the point is to x equals a, the better the approximation will be. In addition, this also works for concave down functions, right? If I were to pick an arbitrary point on this x equal, or on this concave down function, and to draw that tangent line that we've got, we could see that we could similarly use tangent lines to approximate different points on this function. So for example, if that is the x value I'm looking at, we can see that the distance between the two of those would be, relatively small, but if we went closer to that point of tangency, we might see that distance between the function and the tangent line would be even smaller. It's a better approximation the closer it is to the point of tangency. Now, why are we talking about concavity? Sometimes, if we are making these tangent lines and we're making these approximations using tangent lines, we want to know whether the function whether the value that we're getting is an overestimate or an underestimate. In general, we should know that if a function is concave up, it is going to provide an underestimate. It's going to provide an underestimate. And why is that the case? Well, notice that for this tangent line that we have, any point that I pick on this tangent line is going to be below this concave down or concave up function, right? Because this is a concave up function, because it's curving upwards, when I draw that tangent line, the tangent line is going to naturally be below it, which means that the values that I get from it, the approximate values that I get, are all going to be underestimates for the real function. It's going to be an underestimate if that function is concave up. Similarly, we can say that in situations where it is a concave down function, that n shape, if I draw a tangent line, notice that no matter where I draw the tangent line on that concave down function, the tangent line is going to be above the curve. And so because of that, values that I get as approximations from those tangent lines are going to be overestimates. They're going to be overestimates. And so the key piece that we need to be looking at is to determine if it is an over or underestimate. We must look at concavity. So you must look at the concavity of the function. And generally, again, if it's concave up, it's going to be an underestimate. If it's concave down, it's going to be an overestimate. Nice. Let's see how this looks in some examples that we've got. Number one, f is concave up on its domain, and f of 4 is equal to 5, and f prime of 4 is equal to 3. What is the estimate for f of 3.8 using the linear local approximation for f at x equals 4? This phrase, local linear approximation, should really tell you that we are trying to make a tangent line. We're going to make a tangent line, and we're going to use that to approximate this function f of x at x equals 3.8. Now, we generally make tangent lines the same as what we've been doing this whole year. I encourage you to use point-slope form. Point-slope form. And that is the form that is y minus y1 is equal to m times x minus x1. And the reason why we do that is because generally we are given a point and we're given a slope. And this is actually one case, a type of problem where having something in point slope form actually makes the solutions and solving these problems easier than if you were to put them into slope intercept form. Let's see how. So we know the point that it's going through at x equals 4. We see that at x equals 4, the output of the function is 5. So the point that we have is 4, 5 that we're dealing with. And we also see that the slope, the derivative, we know the derivative is the slope of the tangent line. At x equals 4, that derivative is 3. So we know that the slope is going to be 3. So with this information, we're going to put it into our point slope form that we've got over here. And so that is going to be y minus the y value from our point, which is 5, is equal to the slope, our m, which is 3, times x minus the x value from our point, which is 4. So y minus 5 is equal to 3 times x minus 4. This is the equation of our tangent line in point slope form. Now here's the magic. This is a style of problem that comes up often on the no calculator free response section. And so we have 3.8. We're going to want to put that in for our x to use this tangent line to approximate to find the estimate of 3.8. So I'm going to do y minus 5 is equal to 3 times our 3.8 minus our 4. Now, the reason why this is nice, and this is on our no calculator section, is because generally if we're picking a point that is close to x equals 4, or wherever the point of our tangency is, this is going to become a pretty small number, and it's going to be easy to work with even if we don't have a calculator in these problems. So the AP exam really likes giving problems like this on the no calculator section. So we have y minus 5, that's equal to 3. In my parentheses, I do 3 minus 8, 3.8 minus 4. That's going to be a negative 0.2, which, small number, going to be easy to multiply by 3. We're going to get that this is equal to y minus 5 is equal to 3 times negative 0.2, so that is negative 0.6. And then we're going to need to add 5 to both sides. So y is equal to 5 minus 0.6, which is going to be equal to 4.4. That would be my approximation, and I would just sort of give my final answer. We're saying that f of 3.8 is approximately 4.4. That is going to be my final answer for problem number 1. That's my estimate of f of 3.8 using this local linear approximation. Now notice what we did. We actually don't know what the function f of x is here, right? I can't actually find what f of 3 is exactly. They didn't give me the function f of x. All I know in this problem is what the point is, that there's a point on the function f, and I know what the slope is there. So using those two pieces of information, I was able to get an estimate of f of 3.8, even though I don't have the actual function. That's a pretty cool tool. All right, next, B. Is this an underestimate or an overestimate? As we said before, in order to determine if a function is an estimate is over or under, we have to look at the concavity. Because this function is concave up, so since f of x is concave up at x equals 4, we know that in cases where it's concave up, right, if I draw a little concave up function and I draw my little tangent line, that tangent line is below the function. So 4.4 is an underestimate. It's an underestimate of f of 3.8. And again, the entire reason I know that's an underestimate is because this function is concave up. And honestly, if I ever forget whether it's whether it's an overestimate or an underestimate, I just draw myself a little concave up curve and draw that tangent line, and I say, oh, that tangent line is below, so therefore it has to be an underestimate. Cool. Number 2, the function f of x is equal to 5x minus 2x cubed minus 2 is concave down at x equals 1. Find the line tangent, the tangent line of f at x equals 1. All right, so in this case, notice with the information they gave us here, we have neither the point or the slope if we're going to make this tangent line. So I need the point and I need the slope. Point and I need the slope. All right, so to find the point, we know we need an x and a y value. They gave us the x. The y value we're going to get from plugging in here, so I need to find out what f of 1 is. Plugging in that 1 for this function over here. 5 times 1 minus 2 times 1 cubed minus 2. That's going to be equal to 5 minus 2 minus 2. That looks like that's going to be equal to 1. So the point that we're looking at for this problem looks like it's going to be when x is 1, the output is also 1 as well. So 1 comma 1 is our point. The slope they also didn't give us, but luckily for us, we know that to find the slope of the tangent line, that's the derivative. So I'm going to actually find f prime of x, the derivative of f of x, using the power rule. That looks like that's going to be 5 minus 6x squared, and then the derivative of negative 2 is 0, so that goes away. And I'm going to plug in my 1 as well to find the derivative at that x value. So this is 5 minus 6 times 1 squared, so 5 minus 6 is going to equal negative 1. So my slope for this is negative 1. So then, using that information, what is my equation going to be? It looks like it's going to be y minus 1 is equal to negative 1 times x minus 1. this would be the equation of my tangent line in point slope form. So that is number 2, part A. For B, what is the estimate of f of 1.1 using that local linear approximation? So again, local linear approximation is sort of hint, use the tangent line in order to do that. It's a linear approximation. The tangent line, it's a straight line, it's linear. That's what we're talking about at x equals 1. So we're going to take that equation that we had and we're going to plug in x equals 1.1. So y minus 1 is equal to negative 1 times 1.1 minus 1. Again, these are set up really nicely to be able to do without a calculator, so let's do it. Y minus 1 is equal to negative 1 times 1.1 minus 1, which is 0.1. And then we've got y minus 1 is equal to negative 1 times 0.1, which is negative 0.1. And then we're going to add 1 to the other side, so y is equal to 1 minus 0.1, which is going to be equal to 0.9. So f of 1.1 is about, it's pretty close to 0.9. That's going to be our approximation using that tangent line. C, is it an underestimate or an overestimate? Explain. So again, here, key piece of information is the concavity for overestimate or underestimate. Since this is concave down, if we draw a little concave down function, we draw a tangent line. Notice that tangent line is above the function. So since f of x is concave down at x equals 1, not 4, that's the previous problem, f, well actually not f, 0.9 is an overestimate for f of 1.1. So again, I know that's an overestimate because that tangent line is above a concave down function. No matter where I draw that tangent line on a concave down function, it's going to be above it. Cool. Number 3, this is the last one for today. Let's see, the differential equation dy dx is equal to e raised to the y power times 2x squared minus 5x. So remember we did differential equations in the last chapter a little bit. This is saying that the derivative of y with respect to x has this rule, which includes both x's and y's. So let y is equal to f of x be the particular solution to the differential equation with the initial condition that when x is equal to 2, that the f output is going to be 0. Write an equation for the tangent line of the graph at the point 2, 0. All right, if we want the equation of the tangent line, we know we're going to need a point and a slope. They gave us the point. The slope is going to come from the derivative. But they gave us the derivative here. They told us that that's dy dx already. So in order to find the slope, we're going to simply plug in our x and our y value here. We're going to plug in our x is 2 and our y is 0 into that equation. So dy dx, the derivative, is equal to e raised to the 0 power times 2 times 2 squared minus 5 times 2. So that's going to be e to the 0 is going to be 1, right? Anything to the 0th power is 1. So that's 1 times 4 times 2 is 8 minus 10. So that looks like it's going to be 1 times negative 2, which is negative 2. So that's going to be our slope. That's going to be our slope here for our equation. And so here's our tangent line, equation of the tangent line. Y minus 0 in this case is equal to our slope, negative 2, times x minus the x coordinate, which is 2. So we could get rid of that 0 part, just y is equal to negative 2 times x minus 2. That is going to be our equation of the tangent line for A. For B, if we want to approximate 2.2, we're going to plug x equals 2.2 into that equation. So y is equal to negative 2 times, what, 2.2 minus 2. So that's negative 2 times 0.2, which is going to be negative 0.4. So f of 2.2 is about negative 0.4. Bonus question, actually not bonus question. We don't have enough information here about concavity yet in order to determine if this is an overestimate or an underestimate for number 3. But we know if they were to give us that information, we could use that to determine if it is since it's concave up or concave down, whether it is an overestimate or an underestimate. But that is it for today. The rest of our packet is practice. You can try those problems out. As usual, check your answers. Come to class if you've got any questions. And good luck on your mastery check this week. Have a great rest of your day and take care.